Hi there, everyone. We're going to deal with kinematics today, which is the study of motion of a particle. Some of you might already be aware of some kinematics formulas in physics, and I will come back to these ones later towards the end. But some of you might be aware of these SUVAT or STUVA equations, which always involve U, V, A, T, and S. I'll talk a little bit about those ones at the end, but basically those ones always are situations where you have a constant acceleration. So those are particular formats that equations which you deal with in physics, sometimes in maths as well, but where the acceleration is constant. What we're dealing with today are situations where we have, let's have a look here, where we have a particle moving up and down a line, essentially. So it's kind of like an axis. Let's do that a little neater. Kind of like an axis, maybe an x-axis if you like, and maybe it starts at 0, and this particle, maybe like the metro, for example, would be a good example, and that would be moving up and down the line. So you'd have perhaps a certain amount of kilometers that you'd measure off there, and the metro can travel forwards with positive velocity, or it could be moving backwards if it has a negative velocity, and it could even go before 0 as well, if we allowed it to, but it's basically going up and down one scale. Now, we're dealing with situations where acceleration could be non-constant, and we're able to deal with that because we are doing a technique of differentiation. Okay, let's just take that back a second. Right. So first of all, what you need to know is that we deal with vector quantities. So normally we call displacement s, or sometimes it's called x, but we usually use the variable s. So this would be the scale for s. That might be in meters, centimeters, kilometers, whatever. It's usually you'd be using those metric units though. The difference between displacement and distance is that displacement can be positive or negative. In other words, it has a direction. Now, you could put that displacement in 2D or 3D space, but then it will get far too complicated. So, for example, you could have this thing, something moving in terms of moving around in a two-dimensional space. But then we can't have an axis for time. So we're only dealing with situations which are going up and down a line. Okay, so yeah, displacement is distance, which can be positive or negative in our case. Velocity is the same. So for velocity, we use v, and velocity, you might already know this one, it's the change in your displacement over time. Now, your average speed, which we used before, is distance over time, and it's very similar here. We do ds dt. So that's saying what's the rate of change of your displacement at any particular given time. Okay, so if you were coming up with, say, for example, a displacement time graph, then your velocity might be changing over time. It might be positive here, it might be 0 here, it might be negative here, and so on. But we can come up with quite sophisticated graphs for S in this case, right? So velocity is the change in your displacement over time. Okay, and your acceleration, now the kind of the everyday, the layman's use of this term is still the same as what we would use here, acceleration or deceleration. In general, though, for us, we're going to call this just acceleration as to whether it's positive or negative. And that's going to be represented by A, and A is equal to, well, A is the change in velocity with respect to time. So that's your dv dt. So it's how your velocity is changing with respect to time. Now, again, normally, if we wanted the average acceleration, we'd do what's the change in the velocity divided by the time period. But here we're being more precise by looking at curves, by taking the derivative. That, of course, is the second derivative here. So that's d squared s over dt squared. So that's the same thing as differentiating this another time. Okay, so let's have a look at one of these questions then. So let's have a look at the question in the book. There's a little chat, by the way, in the book about this thing here, the average speed. And you can see, by the way, that this is very similar to doing our differentiation from first principles. If we make the two x values closer and closer, or the height, the h, they were making smaller and smaller, essentially, to bring those 2 points together. That's exactly the same thing that's going on here, essentially working out a gradient, then changing it into a derivative. Okay. Oh, one more thing, and that's that there's another really useful formula. Let's just steal this one for a second, okay, before we go on to the question. And that's this thing here. And it says, basically, if you have your velocity or your displacement, let's just look at it again, okay. If it says, if you have your velocity as a function, is given as a function or displacement rather than time, then it's useful to use this formula here. So if velocity is not in terms of t, but it's in terms of s, then this is really useful. So that's an unusual situation, but you'd be saying, well, what's the velocity when I'm at 100 meters, for example, rather than saying what's the velocity at 10 centimeters. So you could have a formula set up like that. Now, if you're going to find your acceleration in that case, they're saying, well, let's use the chain rule. So we still know that acceleration is velocity over time, essentially, dv dt. But if we use the chain rule, we can create this extra ds in this case. And ds dt is your velocity, okay, so that's v. And then dv ds, that would enable us to differentiate our velocity formula in terms of s rather than in terms of t. So if you do have the velocity in terms of s rather than in terms of t, you'll need to use this chain rule in this case as well. So that's kind of useful, but they don't do that in this question here. I'll just talk a little bit around this question. Okay, right, so example 21. Okay, so this one's talking about the height in meters of a rocket projected vertically in the air until it returns to the ground is represented by this function here. Okay, so h is the same as saying s of t. Okay, so s would be your displacement, h in this case is your displacement. And they're saying it's only valid when t is greater than 0, and presumably you'll get something like this. At a certain point, it will stop being valid as well when it hits the ground again. Okay, where t is the number of seconds after the rocket was launched. Right, okay, done. All right, state the height at which the rocket was launched. Okay, so in that case, you're going to need to put in t is equal to 0, because that's the first time that we are recording this trajectory. By the way, the graph of this is going to look like this, okay? So you're going to have your h and your t there, and you'll have something like this. And that's h with respect to time. But what's happening actually is the rocket is simply going up, and then it is coming back down again. So yeah, so it's reaching this high point. So it's going up quickly at the start. It's slowing down. It's getting to this top point. At the top point, it has a velocity of 0, of course. And then it's going to have a negative velocity on the way down and hit the ground. It's not moving to the side in this case. Well, at least we're not told about that. Okay, but it looks like it's moving to the side when you have the time graph, but this is not a side movement. This is a time movement here. Okay, so state the height. So we've done the first part of the question. Part B, find the maximum height reached by the rocket. Now that occurs here. And because it's a quadratic, it's going to be exactly in the middle. There's lots of ways of you doing this, but they want you to use differentiation, of course. So you need to find when does dh dt, in other words, your velocity in this case, when does that equal to 0? So you're going to set, for part B, you're going to set your v, if you like, your dh dt in this case is equal to 0, and then solve for x, or solve for t. Okay, for part C, it says calculate. Part C, it says calculate the velocity of the rocket at 7.5 seconds. So when you get your velocity formula in this case, so when you get your dh dt, that's your velocity, you're simply going to substitute in when t is equal to 7.5. You're going to put that in there, and you're going to work out your answer. It's not difficult. Okay, and the next part of the question says find the other time at which the rocket is traveling at the same speed. So the same speed, right? It's talking about speed though, not velocity. So say, for example, this is, I don't know, this comes out at 3 meters per second. Okay, remember meters per second you can write like this, two ways. Meters to meters, you can use it in an index form as well, which is what I've done here. Now, say the speed comes out as this, or velocity comes out as this, then I'm assuming that at 7.5 seconds, wherever that is, okay, that's your velocity of maybe 3 meters per second. I'm guessing that one. Now, it's not going to, because it's slowing down, it's not going to have that same velocity again. But when on the way down, there will be a point on the other side here where it's coming down and it has the same velocity as well. Sorry, the same speed, but a negative version of that velocity. So what you'll need to do in that case is, say, for example, if you get your velocity, original velocity was 3, you'll need to set your v equal to -3. So the equation you're getting, v, you'll need to set that to -3 and then solve for t. Okay, obviously you've got all of the answers in here, and there we go. Actually, I was way off in terms of the speed there. We have, oh, that's kind of interesting. They've actually done it the other way around. So at 7.5, it was actually beyond the halfway point. So that was -0.33. But then there must have been a point before the halfway point, before it reached its summit at the top point, where it was equal to a positive version of that speed. So with that velocity. So there we go. Right, guys, just one more thing on this one. You can quit off if you want, but just a little bit of theory with the physics, okay? So going back to these SUVAT equations here, okay, so this is a little extra. So we've got these SUVAT equations. Now, I expect that you've seen these ones before. And just if you haven't already, it's just out of interest. It's always a situation with constant acceleration. In other words, if we were going to do a VT graph, your graph would look something like this. And I don't know if you remember, but underneath a velocity time graph is your displacement. Okay, because velocity times by time gives you your displacement. Okay, so these are all situations like this where the change in your velocity divided by the change in your time gives you your acceleration there. And this would give you here your initial velocity of u, and this would give you your final velocity, which we call v, just to be a bit confusing. This is v, this is u, and this is your time here as well. And we always have a constant acceleration here. And you could come up with that graph in different ways. You could come up with something like this instead, but we're not going to. We'll keep it really simple. And basically, all of your formulas come from, so all of these formulas here, these four formulas, these come really quickly from this little graph here. And so, for example, this one, v equals u plus at, is essentially y equals mx plus c. Okay, and s, in these cases, s just comes from different ways of working out the area. So displacement is area underneath a velocity time graph. And this formula, v squared, is just a substitution of two of the formulas. It's a combination of the formulas, but it eliminates t. It's the only formula which is in terms of u, acceleration, and your displacement. Right. So, as I said, this is something a little extra here in situations of constant acceleration, which you may be familiar with from before. This is not what we're dealing with at the moment. We're dealing with velocity is equal to ds dt, and we're dealing with acceleration is equal to dv dt. Right, that's what we're dealing with. Okay, but it is kind of interesting that if you dealt with that rocket situation, so let's take this formula here. So this is displacement. And we could say, let's come up with an example. Let's say u is, I don't know, let's say the thing is chucked up in the air with a velocity of 10 meters per second. T is the time, so that's your variable. And A in this case is gravity, essentially. So gravity is an acceleration. So A is equal to, now acceleration would be towards Earth, so it would be going in a different direction to the initial velocity. So it would be, now in physics you might use minus 9.81. We're going to use minus 9.8 here, again because it's going towards the ground, meters per second squared. Okay, right, now I've set this one up in Desmos, and here we go. If we have a quick look at this, So there we go. There's our graph here. And you can see I've put in, it's been thrown up with a speed or velocity of 10 meters per second. I've put in our acceleration of minus 9.8. And this was just one of those SUVAT formulas here. Okay, so there is our graph. So this x-axis is in fact time. So we can see that at somewhere like just after 2 seconds, this projectile is back down to Earth in this example. Yeah, it starts off with a velocity of 10 meters per second, but it also starts at 0. It starts from the ground. If we put on our velocity formula now, we'll see that we have our constant velocity situation. So there we go. Velocity started at 10 meters per second. Now, at the apex, at the top of this curve, at 1.2 seconds, we can see that the velocity has gone down to 0. So that's how this velocity graph is matching with the quadratic graph. And you can see that down at here, this point here, 2 seconds here, just after 2 seconds, if we put in a height of minus 10, then the velocity graph, which we've drawn on the same axes, gives us out a height of minus 10 there. So it's hitting the ground with the same speed. And you could argue this is not an accurate model because there might be wind resistance in there as well, but this is a decent model. Okay, so there's our situation, and of course we really need to put in limits because the rocket can't go through the ground in this situation. Now, in terms of the acceleration here, the acceleration is always constant here because we have a constantly decreasing velocity because the velocity line is a straight line graph. So if we differentiated this blue line, we will just get this as an answer. So if you can see here, the second derivative is going to give you minus 9.8, which is the acceleration. Now it's not plotting that, but if we wanted to plot that, we'd have to plot equals to minus 9.8. So let's just get rid of this graph. So that would be the black line in this case would be equal to your velocity, so your acceleration. So throughout the blue line, you have a decreasing velocity, decreasing by 9.8 meters per second every second. Guys, hope that's helpful. I wonder if anyone's made it to the end of this video, but thanks for persisting and good luck with the exercise.